In this video, we present an efficient derivative computation for cumulative B-splines on the Lie groups. This work was done at the Technical University of Munich. Continuous time trajectory representations using B-splines are used in many computer vision tasks, but the current implementations require heavy computations and do not achieve real-time performance. In this work, we present a fast and elegant approach to compute time derivatives on the Lie group B-splines. Our recursive formulation requires a linear number of matrix operations and enables fast analytic computation of Jacobians with respect to control knots. This results in faster optimization due to provably lower complexity. Let's have a look how we achieve this.
We denote a cumulative B-spline on a Lie group by x of u, where u is a normalized time variable. Prominent examples of such Lie groups are, for example, the group of 3D rotations, SO3, or the group of rigid body motions, SE3. The spline is defined by a set of control points x0 through xn, which are elements of L. With the log and x mappings, we go from the Lie group to its tangent space and back. Finally, we define a generalized difference vector that gives a notion of the distance between two control points. In RD, this would simply be the vector connecting the two. In order to get an intuition for cumulative B-splines, let's first have a look at the definition in RD. We define the spline P at time u as the sum of control point Pi and a linear combination of difference vectors. The coefficients lambda are defined implicitly by the definition of B-splines and can be found in the paper. Now, if we look at the analogon in a Lie group, we see that the scaled difference vectors are first mapped to L and then multiplied rather than added. Still, in principle, the structure is the same. Taking this definition of Lie group cumulative B-splines, we see easily that x of u can equivalently be defined by a recurrence relation. This is the core idea of our work, so let's see what happens if we take time derivatives in the two formulations. We denote derivatives with respect to u by a dot. In the traditional or baseline formulation, we get a sum of k-1 terms where each of them is a product of k matrices. For the recursive definition, we show by induction that even the time derivative can be defined recursively, needing considerably less matrix multiplications. For second time derivatives, analogous reasoning leads to similar conclusions, with an even larger gain in the number of matrix operations needed. In addition to the time derivatives, we also propose new formulations for the Jacobians of x in the group SO3 of 3D rotations. Again, our formulation only needs O of k matrix operations and is thus much faster than naive differentiation. See our paper for more details here.
To evaluate the proposed approach, we first run a series of simulated experiments. In these experiments, we generate a set of velocity and accelerometer measurements from the spline and set up optimization problem that aims to recover the original trajectory. All the optimizations were done in series and run on the same hardware. We also verified that different formulations converge to identical results. The last column of the table shows speedup factors for different configurations. Our formulation is faster than the baseline in all cases, and the speedup grows with the order of spline. Speedup factors with acceleration measurements are larger than with velocity measurements because the baseline formulation requires a cubic number of matrix operations to compute accelerations and quadratic for velocities, while our formulation needs only a linear number of matrix operations for both. To demonstrate our approach on the real-world data, we use the task of camera MU calibration. We optimize for a set of parameters including the control points of the spline representing the MU trajectory. In this video, you can see the visualization of the optimization process. In the plot below, solid lines are accelerometer measurements computed from the spline that we optimize, and dashed lines are the actual MU measurements. After 12 iterations, the optimization process converges and we can see the spline data fits measurements quite well. Looking at the timing, we compare the split representation that does not couple rotations and translations with the SE3 representation. The results show that the split representation is much faster in all the cases, and the proposed approach to compute time derivatives outperforms the baseline. If we use analytic rather than automatic differentiation, we observe a further speedup. The code for the spline implementations and the presented experiments is provided open source at the link below. Thank you for your attention, and here are the references that were used in this talk.